Since the term technical debt has been introduced, plenty of case studies have been carried out to investigate the types, causes, and consequences of such TD incidents in industry. Most of the time, experts are investigating the principal and interest or time spent on certain technical debt characteristics using questionnaires, or expert interviews in small scales are used to identify new characteristics. Yet, here we encounter some problems. In case of a questionnaire, we need certain experience in the field we are investigating to cover the majority of the answer possibilities. In the other case of expert interviews, the named TD characteristics do not fully represent the frequency or impact of those TD items in the expert's work environment. Therefore, to solve this dilemma, in this study, we focus on investigating the validity of the previous expert interview results of 50 experts from 21 companies by elaborating on the frequency and impact of those TD characteristics identified. Meanwhile, we examine whether the avoidance of TD depends on distinct characteristics of the product or the company, for example, the output quantity, external conditions or requirements, or internal regulatory mechanisms. So the potential benefit of this work is the report of the real impact of TD characteristics on practitioners in the field of mechatronics. That means an interdisciplinary environment of mechanical, electrical, and software engineering. Shortly, to introduce myself, I'm Fanny B. I received a Master of Science degree in Mechanical Engineering in 2019, and I'm researching towards my PhD degree since with the Institute of Automation and Information Systems at the Technical University of Munich with Professor Vogelhäuser, who is also the second author of this study. My research interests focus on identifying and measuring technical debt issues in mechatronic systems. As mentioned, we have carried out a prior study where we could identify that requirements TD, architectural TD, and design TD were the three TD types that were named most frequently in the mechatronic product lifecycle, next to infrastructural TD, which cannot be assigned to a distinct lifecycle stage. Furthermore, we could identify that different disciplines in mechatronics suffer from different TD types. For example, software engineers in an interdisciplinary environment appear to suffer more from requirements TD, in contrary to previous studies in software engineering that focused on code TD, architectural TD, and test TD. After we have gained these insights on how TD characteristics are represented in mechatronic systems, we still don't know whether or at which point the previous results represent the actual state of TD to experts, which represent our first research question. Furthermore, we wish to investigate what the TD types, causes, and symptoms with the most considerable frequency and the most significant impact are. How does the discipline of the expert affect the frequency and impact of TD characteristics? And which corporate and organizational structures encourage the avoidance of initiating TD? From the 50 experts involved in the previous study, we were able to receive answers of 15 experts. For the questionnaire, we have used a Excel form where we included the encountered TD types, causes, and symptoms. Enlarge the options with the causes and symptoms by current studies in software engineering, which are marked gray. These experts could give their rating on the frequency and impact on a Likert scale from 1 to 6. Also, the voting of 0 is possible in case the experts cannot relate to the item. In another section of the interview, experts were asked to report whether it depends on 5 distinct characteristics to avoid the initiation of TD. For the analysis of TD types, first we have mapped their frequency to impact. Requirements TD is the most dominant TD type regarding the frequency and impact in mechatronics, followed by infrastructure and variance TD. Architectural and design TD proved to be the two remaining TD types with above average frequency. So what we could identify is one cluster where high frequency TD types with large impact on the system is represented. And what we could see here is that the first four TD types, requirements TD, infrastructural TD, architecture TD, and design TD, were also the four most frequently mentioned TD types in the prior study, where variance TD has only had 4 mentionings in the prior study. So, on the other hand, we have identified another cluster with 4 TD types with lower frequency and also relatively low impact on the system, which is code TD, defect TD, documentation TD, and versioning TD. As we have had only one expert in the domain of electrical engineering and software engineering, as well as 2 experts in the domain of all 3 disciplines, we have excluded these data from our analysis. However, we provided them also in the paper in case someone wants to know details about their votings. For a deeper discipline-related analysis here, we provide 4 columns. The first one represents the general occurrence of the 50 expert interviews. In the second one, we selected the 15 experts who participate in this study and their occurrence of TD types in the previous study. And later on, the blue one and the orange one represent the average frequency and impact of the 15 experts in this study. We have provided the distribution of each of the disciplines: mechanical engineering, electrical engineering, and software engineering. Compared to the results of the previous study, we could identify that for mechanical engineering, the overall frequency and impact is lower than for the other 2 disciplines. Maybe because traditionally it is the first discipline in the life cycle to be carried out. For design TD, it receives high votings in frequency and impact, while architectural TD and maintenance TD are those with the highest impact. In electrical engineering, there are way more types to be pointed out, yet we want to focus on software engineering in this presentation. Here we could see that 3 of the 4 most mentioned TD types get high rankings, namely requirements, infrastructure, and architectural TD. Furthermore, variance TD, which was only occurring once in the study before, has received one of the highest rankings in frequency and impact. Therefore, the conclusion of the previous study can be verified. Software engineering experts that work in an interdisciplinary field are bothered by different TD types than software engineers that work at their domain in isolation, namely by requirements, infrastructure, and also variance TD. Now we take a closer look at the TD causes. We are extremely grateful that all 15 experts have took the time and reported their experience with all TD causes and symptoms we have offered, as there are plenty of them, as you can see. Next to the most common time and cost-related issues, we could also identify causes that describe the technical solution selected as the best possible at that time. In electrical engineering, great complexity as well as the lack of refactoring seem to be a really important cause, both in frequency and impact. Furthermore, for all 3 disciplines regarding TD, the extra effort is simply underestimated. Additionally, we have identified 2 important interdisciplinary TD causes, namely the purple marked ones. Experts feel that they only have a limited view on the decisions made in their companies and the system itself. Here, silo thinking in between the disciplines need to be addressed and avoided. Also, electrical and software engineers often suffer from mechanical engineering, that is the most established discipline in the industry. As for most of the interviewed experts in the companies, it is more frequent that the root of the company is in mechanical engineering and has been evolved in times of digitalization. The results of the TD symptom analysis can be found in the paper itself, as the interpretation of these would exceed the limit of this presentation. Last but not least, we wish to present the structures encouraging the avoidance of TD incidents initiation. The experts state that the larger the input quantity, the more they prevent TD from occurring. Furthermore, uncertain market conditions and the fact that a product involves all three disciplines of mechatronics are structures that positively affect TD from occurring. So we are pretty aware that this study only covers a sample of 15 selected questionnaires from the industry, which merely gives limited generalizability. Yet the comparison of the 15 questionnaires to the answers of the same sample in the expert interview in the previous study offer great insights, at which point the TD characteristics diverge and reveal evidence for future technical debt management. We thank you for your attention and for your interest, and feel free to ask your questions. Thank you.
Hello, good afternoon, everyone. Welcome to this second session. Our first paper of this session on TD characteristics will be given by FunDB, and the topic is on the way that they see and perceive technical debt in the domain of producing mechatronic products. So, Fundi, the floor is yours.
Okay, thank you so much. Thank you for the introduction. So, hello everyone, I'm Fandi. Actually, it's my first conference to join, and I'm doing research in identifying technical debt in mechatronic products and production systems, and somehow it's really an honor to be here for the first time. So what we have done is we investigated the frequency and impact of technical debt characteristics. So what we understand technical debt characteristics is, for example, TD types, TD causes, symptoms, and consequences. And the domain of mechatronic products might not be really familiar to you all, but it involves three disciplines during the development, production, and also maintenance and recycling process. And these are the mechanical engineering, electrical engineering, and software engineering. So we have all three domains that makes mechatronics. And we were somehow at the start of the research, and we didn't know how to approach, because in software engineering there are already a lot of papers investigating these characteristics, but we didn't know at which point they apply to our systems, and also are they applicable, or can we adapt some results? So we somehow started from scratch. We knew that some TD types, we had them as well. For example, requirements TD or test TD. These are like the two most famous ones of which we knew. But yet we didn't know, are there more TD types? Is the frequency different than in software engineering? And how can we ask the experts to give us this information? So in the beginning, we were thinking about expert interviews, because then you get, you can elaborate on more detailed information, but it takes a lot of time, and you don't know whether you can somehow code these information analyze them in a structured way. But also for a questionnaire, we had some problems because we didn't know which options we should give them. So then we decided to do a two-step model. So in the first one, we decided to do a lot of expert interviews. This is what I've done in my master thesis. So during 6 months, I was interviewing 50 experts from 21 companies all around Europe. And in the second step, when we have coded everything, then we were letting the same amount of experts, or we were asking the same amount of experts to rate at which point the distinct TD cause or symptom or consequence would really reflect also the frequency and the impact in the whole company or in their working environment. So it was a long introduction, but just let's jump into the results. So as you can see, maybe here in the beginning, these are the results which we have received from the expert interviews. And we have found out that we have a high frequency at the beginning of the product lifecycle. So here in the bottom, you can see the product lifecycle. This is like derived from the B model of software engineering. You start with the requirements, design, implementation, and later on you have in mechatronics the assembly, testing, commissioning. If you have finished up your machine and you deliver it to the customer, the startup phase, operation and maintenance, and also later on the upgrade and retrofit. And what we could identify is that we really have issues here in requirements TD, architectural TD, and design TD. And when we have started the interviews, we have clustered a lot of things to infrastructure TD, for example, the processes or the guidelines. So we were not distinguishing these kind of TD types. And if we take a closer look at the different disciplines in mechatronics, so we have did the classification, for example, the experts work solely in mechanical engineering, then here's in this. And if he is, like, for example, engaged in all three disciplines, then he belongs to this row. And we could see that depending on the expert's discipline, we have different TD types. So, for example, the electrical engineer has a lot of issues with design TD. And what was like mostly surprising to us is the software engineers. They were suffering from requirements TD and infrastructure TD, so regarding processes, guidelines, and the environment, rather than what the software researchers have been focusing, for example, code TD, test TD, architectural TD. So somehow, if the software engineer works interdisciplinary, then he is suffering from different types of technical debt. So in the next step, we didn't know whether this this graph we have generated is also reflecting the actual behavior of technical debt in the company, because the interviews were like between 30 and 40 minutes. So probably the expert has the time to describe 2 to 3 technical debt incidents, but if the technical debt incidents, which were the most important to them, or they remember the most, are also the ones which are most frequently appearing in their work environment. We didn't know this fact. So in the next stage, we were working out a questionnaire. So it was an Excel form. We had a lot of TD causes, symptoms, and consequences. We send it to the 50 experts, and 15 of them, unfortunately only 15, but we are somehow really happy that they still answered, because these results are now presented in this paper. So what we have mapped here in the first graph is the average impact to the frequency. And what we can see here now is that there are some technical debt types, for example, requirements TD as the most prominent one, also infrastructure, architecture TD, design and variant TD. These are those TD types with large impact on the system. So large impact and high frequency. And on the other hand, there are like down there, you have some ones that are, documentation is appearing more frequently, but it doesn't have such a huge impact reported by the expert. So they are like, relatively low here in the frequency and impact matrix. And if we continue, then we were also comparing those TD types which were mentioned in the first round. So this is the entire amount of technical debt types which were mentioned in the first study in the expert interviews. This light green one is the amount of technical which were mentioned by the 15 experts in the first round. And then here, the blue and orange one are the results of this study. Due to the low participation rate of electrical engineering, software engineering, and all three disciplines of mechatronics, we presented these results, but we don't further discuss them because, here we had only one expert and here we had two. So what we could see clearly is that compared to the results before, we have for mechanical engineering design TD, which is like high in frequency and impact, as well as architectural TD and maintenance TD. They are really impactful to the experts in mechanical engineering. For the electrical engineering, we have infrastructure requirements, architecture, some more. And for the software engineers, we didn't expect this to happen, but after they have sent us the results, we have here really high votings in the requirements, because so in the mechatronic development, most of the time the companies are rooted in mechanics. So the CEO is from mechanical engineering, the project managers from this discipline, and most of the time they are like more focused on how the product should look like, and not how should it work. So the structure is pretty clearly defined, but the function isn't. So the software engineers have large problems deriving test cases or even programming their code, because it's not common. So from my interviews, from my knowledge, I know it's not common to have like clean requirements for the software engineer. And also the infrastructure suffers a lot, and also architectural TD and variance TD. So you have a lot the copy paste modify strategy there. So if we move on to the TD causes, so this is the entire list of the causes we had in our questionnaire, and we're glad that all the experts have given fully answers to these to this list of causes. So a part of them we have gathered them from our expert interviews before, but also from several papers from software engineering. We have enriched these TD causes. And what we could see, of course, the typical causes, lack of time, we need to save costs, it is suboptimal, but it was the best at that time, great complexity. Also, here refactoring seems to be wasted time, or extra effort is simply underestimated to be one of the most prominent ones. But also, for mechatronics, we have identified that there are two interesting ones. For example, no holistic view. So this is maybe rooted to the silo effect of working interdisciplinarily, and you only focus on improving your segment or your discipline, but you don't somehow the developers don't care. The mechanical engineering ones, they don't care if they modify their structure. Maybe it affects electrical engineering. So either they don't want to have the holistic view, or they don't get it due to the system. And also here what we have, especially prominent for the software engineers, is the TD cause one discipline is more established in the industry. So this is the same effect what I have described before. The root is in mechanical engineering. So sometimes the software engineers are taken into the group really late, or some information are not handed over. Software is the last step, and it's really easy to implement because you have like low-code platforms or no-code platforms somehow. This is still inside the head of the mechanical and electrical engineers. I don't know whether you can relate to these problems. So these are the things we have encountered. And also, last but not least, we were investigating 5 structures. So what you can see here is, for example, large output quantities. So the question we asked ourselves is, are there any structures that encourage the engineers or entire companies that they avoid initiating technical debt? And what we have found out is, for example, quantity is one of the most important factors to prevent initiating technical debt. And also, in case of uncertain market conditions, the experts are paying more attention, not initiating debt. And also in mechatronic development, so if you are developing a product which involves more than one discipline, it is also here rated as we intentionally avoid here initiating that. And also we evaluated variance and whether TD is centrally tracked by, for example, a controlling department compared to the own project. So these are the first results of our empirical study, and we from the chair are quite sophisticated with the results. And for the future research in the field of mechatronics, we wish to analyze more the cause and effect relations of these TD characteristics to identify metrics for mechatronic systems. So thank you very much for your attention, and we're like open for questions. And thank you so much for having me here.
Andy, thank you for the very interesting presentation. We have 2 questions actually from the audience. So I start from the one by Tushar. When you were checking the technical debt issues from software engineers, have you checked if they were pointing to software engineering artifacts, or the scope was extended to other artifacts like mechanical engineering artifacts like CAD files or RAM files or things like this?
So we were not, if I had understood it correctly, it's regarding the files, whether I have investigated different files, right? Or
as I understand it, yes, different files that are developed by different disciplines. So if TDs has been
Actually,
found in files of different disciplines like mechanical engineers, or everything was source code.
So we have not investigated the files from the engineers. It's only the report of their experience in working in their company. So of course, later on, if we wish to develop a technical debt management tool, we have to link all these files, but not only the files, also, for example, the PLM or the MES systems, which contain more information on process to elaborate on real metrics, but we have not we have not asked them to give us some files to identify technical debt, if this answers your question.
Thank you. And also the other question comes from Daniel. He asks if the challenges faced by the software engineers, for example, related to infrastructure, might be due to their lack of knowledge in specific domains.
So from my interpretation, I don't think so, because somehow, if you're developing a mechatronic product, if you get a for example, you have a robot, then the robot should move from here to there. Else, if you move from here to another place, then it's false. I think if you explain it to the software engineer which code you have to implement or what the robot has to do in that case, it is somehow quite clear. I really don't think that the software engineer in this case lacks information about the other two disciplines. It's more about the engagement of